So I'm actually really excited for this section on power series, largely because it's going to bring together a few things that we've been talking about, and hopefully start to justify why we're spending so much time on this idea of a series. So I want to go way back to multiple months ago when we were talking about approximating the area under a curve using things like the left-hand approximation or the trapezoid rule or those types of things. So if we have some function, so here's my x, y, and x and y axis. If we have some function, let's say that looks like this, and I want to approximate what it's doing on a certain range. So let's say from this A to B. We've talked in the past about the different ways that we can talk about how much area is under this curve. We can approximate what this function is doing by, for example, using the left-hand rule, which says, all right, whatever that left-handed point is, let's just pretend that the function is that constant value the whole way through. And at least for this picture that I've drawn, that looks like a pretty bad estimation. And yes, we've talked about how if we use smaller intervals, we can actually approximate this to a higher degree of accuracy. But another thing that we can do is use a more complicated function. So I would say that this function looks a lot like the function 1, so some constant function. If we allow our function instead to be something, let's say, linear, then instead of that, we might be approximating, and this is where the trapezoid rule comes in, we might be approximating the actual function, let me call that f of x, but with some other, in this case, linear expression. So let's say that this looks like 1 plus x. And sort of towards the end of that, we didn't spend much time with it. We talked a little bit about Simpson's rule, which in practice, rather than using the left endpoint or the right endpoint or the midpoint or any of these things, it uses a combination of a few of those. And what it ends up doing is drawing a parabola over the region in question. So let's say, oh, that doesn't look much like a parabola, but you use your imagination a little bit. This might be something like 1 plus x minus x squared. So this is a second degree polynomial, meaning that we're going up to an x squared term. And as we can see, even with this kind of questionable drawing, we can see this is a much better approximation for what our function is doing over this range from A to B. And we can sort of imagine, oh, if we allowed this to be a cubic, maybe it would be even closer. F of x sort of already looks a bit like a cubic. Maybe the behavior would match even closer. I would like to point out, and this actually was intentional, that while it may be almost exact or even actually exact for some of these points, as we get further and further away of sort of the focus, whatever that means, we're going to be sort of less and less accurate. So the fact that we had this amount of error here was an intentional thing. Okay, so the general idea of power series is that we are going to talk about a function f of x using a series of polynomials. In other words, we're going to approximate f of x with an infinite degree polynomial. So each of these intermediate pieces are like our partial sums. We're approaching the actual function in question f of x. So you might notice that, all right, we started off with a 1, and that was okay. And then the 1 plus x was better. 1 plus x minus an x squared. Maybe it needs a 1 plus x minus x squared plus 2x cubed term to make it even more accurate. But there is some way of taking higher and higher degree polynomials and having this limit towards our function f of x. Okay. We're going to talk a lot more over the next couple weeks about how we come up with what these coefficients are. That's chapter 10 is all in Taylor's series, which is working with these types of things. But before we do that, I want to show you an example that isn't a questionable drawing. All right, so hopefully you can now see this one. So what we have here is a GeoGebra model, and the function in question is this cosine of x term. So our f of x is cosine of x, and we want to approximate this with higher and higher degree polynomials. So the first step is to say, all right, we're going to approximate what this function is doing, and we're sort of focused where x equals 0. We want to say, all right, how can we approximate this function? It's like, well, let's take the constant function that lines up at x equals 0. So everything's centered at x equals 0. And in this case, this constant function is sort of the best we can do. As we see, like as we get further away from x equals 0, we actually get pretty far off. All right, what if instead of a constant function, we allowed it to be a quadratic? If instead we used 1 minus x squared, this ends up being x squared over 2. Well, this quadratic looks a lot better. That, like, especially near 1, it looks like it does a pretty good job of hugging this line. If we zoom in, we might see that, well, it's actually a little bit off. There's a little bit of error here, and you have to zoom in pretty far when you're really close to 0. But we can see that for the most part, this is actually a pretty good approximation in the neighborhood of 0. But what I wanted to point out was if we allow higher and higher degree polynomials, if instead of just going up to x squared, if we allowed it to go up to x to the 4th, we can see that we actually sort of hug this cosine curve a little bit more closely. And as we allow higher and higher degree polynomials, we're going to see that this gets closer and closer to mimicking what's actually going on. And we're going to get sort of multiple components of this cosine curve. And so we actually get sort of about 3 or so periods of this harmonic, of this periodic function. Okay, so this goes up to a 20th degree polynomial. You can imagine if we kept going, this would get closer and closer. So the general idea behind power series is that we are going to let the allowable degree of the polynomial go to infinity. So in the limits, as we keep adding terms to this, we're going to get some infinitely long polynomial expression. Right? It's a series. It's the sum of infinitely many terms, which actually ends up equaling the function itself. Right? So that's sort of the goal. That's what we're working towards. We have a few more things to talk about before we get to how exactly we calculate these things. But our general goal is to be able to work with these infinitely long polynomials rather than a function that might actually be kind of tough to work with. We spent a little bit of time at one point talking about how there are functions out there that can't be integrated. This is a way to get around that. Rather than working with the function itself, you can look at its power series. You can look at this sum of polynomial functions and work with that instead.